We spend so much time talking about what to do during an earthquake, right? But what about before it even hits? How do we even know which buildings are at risk?
Yeah, that's a huge problem. I mean, just think about the sheer number of buildings out there. How do you even begin to figure out which ones might be dangerous in an earthquake?
That's exactly what we're diving into today, this idea of rapid visual screening.
RVS.
RVS. It's kind of like a first response team, but for buildings. A way to quickly assess which ones might be in trouble seismically.
So it's like a quick checkup, just to see if there are any obvious red flags.
Exactly. And we're going to use the FEMA P-154 report to guide us through it, specifically the third edition. It's called Rapid Visual Screening of Buildings for Potential Seismic Hazards, a handbook.
FEMA, that's the Federal Emergency Management Agency, right? They're the folks who deal with all sorts of disasters.
That's them. And this handbook is all about identifying and keeping track of buildings that might be hazardous during an earthquake.
Makes sense. I mean, you got to know what you're dealing with before you can even start to fix it. And this handbook is the third edition, which means they've had a lot of time to refine the process.
That's right. It's not just some theoretical document. It's been tested and updated based on real-world experiences and research.
Including the lessons learned from places like Oregon and Utah that have already done some pretty extensive screenings.
Exactly.
Yeah.
So today we're going to unpack the core ideas behind rapid visual screening. What it is, why it's so important, what its limitations are, and how it's actually put into practice.
Sounds like a plan. Let's start with the basics then. What exactly is rapid visual screening?
Okay, so imagine this. You're walking down the street looking at buildings, trying to figure out which ones might crumble in an earthquake.
Okay, I can picture that. So you're basically doing a quick scan to see if there are any obvious signs of weakness.
Pretty much.
Yeah.
That's the essence of rapid visual screening. It's a fast, primarily visual assessment of a building, mostly from the outside, to see if it might be at risk during an earthquake.
Gotcha. So you're not going in and doing a full structural analysis at this point.
Not at all. This is just the first step, the triage, if you will. The goal is to spot those buildings that need a closer look from a qualified engineer.
So it's like a filter then, to quickly narrow down the buildings that need further investigation.
Exactly. They basically categorize buildings into two groups, those that seem okay and those that might be hazardous and need more attention.
Makes sense. How do they decide which group a building falls into? Is there like a grading system?
There is. They use a scoring system, and if a building gets a score of 2.0 or less, that's when the alarm bells start ringing.
2.0 or less.
Got it.
But what does that number actually represent in terms of real-world risk?
Okay, so let's say a really strong earthquake hits, the kind that doesn't happen often but can cause serious damage.
Right, the big one, so to speak.
Exactly. That 2.0 score basically means there's a higher than 1% chance that the building might totally or partially collapse in an earthquake like that.
Wow. Okay, that puts it into perspective. So a low score means there's a real risk of the building literally falling apart.
Right. And when we talk about collapse, we're talking about the whole structure failing. The walls, the roof, the supports, everything.
Yeah, that's definitely a serious concern. So speed is obviously a key factor here, but why is this rapid approach so important?
Well, think about it. If you had to do a full, detailed analysis of every single building in a city, it would take forever and cost a fortune.
True. You'd need an army of engineers and years to get it done.
Exactly. So rapid visual screening is a much more efficient way to get a handle on the overall risk. It's quick, and it doesn't require a structural engineer for every building, at least not initially.
So you can cover a lot more ground quickly and get a sense of which buildings might be the most vulnerable.
Right. And the methodology is designed to be as clear-cut as possible to reduce ambiguity and make it easier for the screeners to make quick decisions.
Plus, we've been doing this for a while, right? Like you said, this is the third edition of the handbook.
Over 25 years of experience has gone into this process, and they're constantly updating it based on new research and findings.
Okay, so it's not a perfect system, but it's a pretty robust and time-tested approach.
Definitely. But of course, it does have limitations.
Right, because you're only looking at the building from the outside and doing a quick assessment. Yeah, there's got to be stuff you miss.
Exactly. You might not see a dangerous crack hidden inside a wall or a weak support beam in the basement.
So it's possible that a truly hazardous building could slip through the cracks.
It's possible. That's why it's so important to remember that this is just a preliminary screening. It's not a guarantee that a building is safe.
Makes sense. So it's like a first line of defense, but not the be-all and end-all.
Exactly. And the accuracy also depends on the experience of the screeners and the information they have about the building beforehand.
Gotcha. So it's not just about the method itself, but also the people doing the screening and the data they have access to.
Right. Speaking of people,
Right.
let's talk about who's actually involved in this whole process. Who are the players in this RVS ecosystem?
Okay, so at the top, you've got what they call the RVS Authority.
The RVS Authority. That sounds kind of official.
It is. They're the ones who decide to do the screening in the first place. It could be a city council, a school district, a state government, whoever's responsible for a bunch of buildings.
So they're the ones who say, hey, we need to figure out which of our buildings might be at risk.
Exactly. And once they make that decision, they usually appoint a program manager.
The program manager, what do?
They're like the quarterback of the whole operation. They develop the plan, figure out the budget, make sure everything runs smoothly.
Okay, so they're the organizers, the ones making sure everything gets done.
Right. And then you've got the technical expert, the supervising engineer.
Ah, so this is the person who actually knows all the ins and outs of seismic safety.
Exactly. They're usually a structural engineer with experience in seismic evaluation. They help select the data collection forms, make sure everything's up to code, and are available to answer questions from the screeners.
Okay, so they're the brains of the operation providing the technical guidance.
Right. And sometimes the program manager might also be the supervising engineer if they have the right qualifications.
Interesting. So it's not always two separate people.
Right. And then you've got the folks who are actually doing the screening, the screeners themselves.
So these are the ones out on the streets looking at buildings?
Yep. They could be engineers, architects, graduate students, even people with a general construction background as long as they've had the proper training.
So it's not necessarily a job just for seasoned professionals.
Right. For the basic level 1 screening, you don't need a PhD in structural engineering. But for the more in-depth level 2 screening, you definitely want someone with more experience.
Okay, so different levels of expertise for different levels of screening.
Exactly. And the experience of the screeners can also influence how closely the supervising engineer has to review their work.
That makes sense. So it's a team effort involving a range of skills and knowledge.
Absolutely. Now let's talk about the process itself. How does this whole screening thing actually work from start to finish?
Or let's break it down step by step.
Well, it all starts with planning.
Of course. You got to have a plan.
Right. You need to figure out what you're trying to achieve, what types of buildings you're going to screen, what information you need to gather.
Makes sense. So you're basically setting the scope and objectives for the whole program.
Exactly. And then comes the pre-field data collection.
Pre-field. So this is before anyone even sets foot near a building.
Yep. This is where you try to learn as much as you can about the buildings beforehand.
Like doing your homework before the test?
Exactly.
Yeah.
They'll look at assessor's files, building permits, historical maps, even just do some good old-fashioned internet searches.
Wow. So they're really trying to get a complete picture of the building's history and characteristics.
Right. The more information they have up front, the better. And they can even use this information to pre-fill some of the data collection forms.
Oh, that's smart. Saves time in the field.
Exactly. And then, of course, they need to have a good system for keeping track of all this information.
So they don't lose anything in the shuffle.
Right. It could be a simple spreadsheet or a more sophisticated electronic database.
Gotcha. So once they've done all that prep work, it's finally time to hit the streets.
Yep, that's when the actual field screening begins. We'll focus on level 1 first, since that's the initial assessment.
Right, so the screener is standing in front of a building. What are they looking at? What's catching their eye?
First and foremost, they're trying to figure out the FEMA building type.
The FEMA building type, what's that?
It's basically a way of classifying buildings based on their structural materials and how they're designed to resist earthquakes.
So like wood frame, steel frame, concrete, and so on.
Exactly. There are 17 different FEMA building types, each with its own unique code.
Okay, so they're categorizing the building based on what they can see about how it's put together.
Right. And they're also noting down basic information like the address, the number of stories, the estimated floor area.
So they're creating a profile of the building.
Exactly. And they'll take pictures from different angles and maybe even sketch out some key features.
Okay, so they're documenting the building visually as well. What about how the building is used? Does that matter? Like, is a school scored differently than an office building?
Well, they do record the occupancy type, whether it's a residence, a commercial building, a school, whatever, but it doesn't directly affect the structural score in a level 1 screening.
So how the building is used isn't a factor in the initial assessment?
Not for the basic structural score, but it's still important information to have, especially if they need to prioritize certain buildings for further evaluation later on.
Right, because a school full of kids might be a higher priority than an empty warehouse.
Exactly. Now, what about the building's surroundings? Do they look at what's next door?
That's a good question. What happens if a neighboring building collapses onto the one they're screening?
Yeah, that's a major concern. One thing they look for is the potential for seismic pounding.
Seismic pounding, what's that?
It's when two buildings are so close together that they can actually smash into each other during an earthquake.
Ouch, that sounds bad.
It can be very dangerous. The screeners will check the distance between buildings and see if their floors line up or if one building is much taller than the other.
Makes sense. So they're looking for any potential collisions.
Right. They also pay attention to buildings at the end of a block because those can sometimes behave differently during an earthquake.
Interesting. And what about the building itself? Do they look for any weird shapes or irregular designs that might make it weaker?
Absolutely. They look for both vertical and plan irregularities.
Vertical and plan. Can you explain those?
Sure. So vertical irregularities are things like a soft story where one floor has a lot less support than the ones above it. Maybe it's got big open spaces or fewer walls.
Like a ground floor with a parking garage underneath?
Exactly. That can be a weak point in an earthquake. They also look for big variations in story height or buildings built on a slope.
Okay. And what about plan irregularities?
Those are weird shapes in the building's layout, like an L shape or a U shape with those reentrant corners.
Ah, so anything that makes the building shape more complex?
Right, because those irregular shapes can cause uneven stresses during shaking. They also check for things like large openings in the floors or walls or places where the load-bearing walls don't line up properly.
So they're looking for anything that might create a weak spot in the structure.
Exactly. And of course, they'll also look for any obvious hazards like loose bricks, cracked walls, unanchored chimneys, that sort of thing.
So they're doing a thorough visual inspection, noting down anything that looks risky.
Right. They're trying to get a sense of the building's overall vulnerability to earthquakes.
Okay, so they've gathered all this information. Now, how does it get translated into that numerical score we talked about earlier?
Right. So the heart of the level 1 scoring is the basic score.
The basic score, what's that based on?
It's a predetermined score that depends on two things: the FEMA building type and the seismicity of the region.
The seismicity. So how likely is it that an earthquake will happen in that area?
Exactly. They divide the U.S. into different seismicity zones based on the level of earthquake risk.
So a building in California would probably have a different basic score than a building in, say, Kansas.
Right, because they face very different earthquake threats. So the basic score reflects the average expected performance of that type of building in that specific earthquake zone.
Makes sense. So it's like a starting point based on the building type and location.
Right. And then they add or subtract points based on specific features of the building and its surroundings.
Those are the score modifiers we talked about, right?
Exactly. And there are modifiers for all sorts of things, like whether the building was built before modern seismic codes were adopted, or whether the soil conditions are particularly good or bad.
So they're fine-tuning the score based on the specific details of the building and its environment.
Exactly. And to get the final level 1 score, they add up the basic score and all the applicable modifiers.
And what happens if that final score is 2.0 or less?
That's when they recommend a detailed structural evaluation.
So a professional engineer needs to come in and take a closer look.
Exactly. But it's not just the score that can trigger a detailed evaluation.
There are other factors, too.
Right. If they spot certain hazards during the screening, like a high risk of pounding or significant damage to the building, even if the score isn't that low, they might recommend a closer look.
So it's a combination of the score and the specific risks they observe.
Exactly. They want to make sure they're not missing anything important.
Now, you mentioned a level 2 screening as well. How is that different from level 1?
Level 2 is a more thorough investigation. It's
Yeah.
usually done by a structural engineer or an architect with specific experience in seismic design.
So it's a step up in terms of expertise.
Right. And they might actually go inside the building to get a better look at the structural system.
Ah, so they're not just looking from the outside anymore.
Right. And they use a different data collection form for level 2. It's more detailed and allows them to make more precise adjustments to the score.
So they're really getting into the nitty-gritty details of the building's construction.
Exactly. For example, they might look at whether the building has multiple load paths, which means it's better able to distribute forces during shaking.
Ah, so it's less likely to collapse if one part fails.
Right. They might also check for specific types of bracing or connections that are known to be stronger in earthquakes.
And I bet they also look more closely at those pounding risks we talked about earlier.
Definitely. In level 2, they use actual measurements and calculations to determine the minimum safe distance between buildings.
So it's not just a visual estimate anymore.
Right. They're using engineering principles to make a more accurate assessment.
And if they find that the buildings are too close together?
Then they'll adjust the score accordingly and might recommend some mitigation measures.
Like what?
Well, it depends on the situation, but it could involve things like strengthening the buildings, adding extra bracing, or even increasing the separation distance.
So they're looking for ways to reduce the risk of damage.
Exactly. And in level 2, they can also take into account any seismic retrofits that have been done to the building.
Retrofits, you mean like upgrades to make it more earthquake resistant?
Exactly.
Yeah.
If a building has been properly retrofitted, they'll give it a higher score.
That makes sense.
Yeah.
So they're recognizing that the building is now stronger than it used to be.
Right. And they'll look for evidence of specific retrofitting techniques, like adding bracing to cripple walls or installing new shear walls.
So it's not just about identifying risks, but also about acknowledging the improvements that have been made.
Exactly. Now, throughout our conversation, we've talked a lot about seismicity. How does that play into the whole RVS process?
Yeah, it seems like knowing how strong the earthquakes are likely to be in a particular area would be pretty important.
It's absolutely fundamental. The whole RVS methodology is built around the concept of seismicity.
So they're not using the same standards for California as they are for, say, Maine.
Exactly. The U.S. is divided into 5 different seismicity regions from very high to low. And the basic score for each building type changes depending on which region it's in.
Makes sense. So a wood frame building in a high seismicity zone would have a lower basic score than the same building in a low seismicity zone.
Exactly, because it's facing a much greater threat. And some of the score modifiers also change depending on the seismicity level.
So the whole scoring system is tailored to the specific earthquake risk of the area.
Right. It's all about making sure the assessment is relevant to the actual hazards.
Now, you also mentioned an electronic scoring method. What's that all about?
It's basically a way to get a more precise assessment of both the seismicity and the soil conditions at the building's location.
So instead of just using the broad regional categories, they're looking at the specific spot where the building stands.
Exactly. They can use the building's GPS coordinates to access detailed seismic hazard maps and soil data.
So they're getting a more granular view of the risks.
Right. And this can be especially useful in areas that are on the border between 2 seismicity zones, or where the soil conditions vary a lot within a small area.
So it's about fine-tuning the assessment to be as accurate as possible.
Exactly. And there are various software tools and apps that can help with this. FEMA even has its own software called Rover.
Sounds pretty high-tech. So it seems like technology is playing a bigger role in RVS these days.
Definitely. It's helping to make the process more efficient and accurate.
Now let's talk about some real-world examples. How has this all been put into practice?
Well, the FEMA P-154 handbook actually includes a couple of hypothetical scenarios based on real-world experiences.
Oh, that's cool. So we can see how this actually plays out in a community.
Right. One scenario is called Any Place USA, and it focuses on a level 1 screening of 1,000 buildings.
So a pretty large-scale assessment.
Right. And they emphasize the importance of thorough pre-field data collection and using an electronic database to manage all the information.
Makes sense when you're dealing with that many buildings.
They also talk about how to adapt the data collection forms to meet local needs and how to determine the key seismic code dates for the area.
So it's a practical guide to setting up and running an RVS program.
Exactly. And another scenario called Any State USA looks at both level 1 and level 2 screenings of school buildings across an entire state.
So they're focusing on a specific type of building in this case.
Right. And they highlight how to deal with different seismicity levels within the state and how to use both levels of screening to prioritize the most vulnerable buildings.
Interesting. So they're adapting the approach to the specific context.
Exactly. And they even talk about how to incorporate data from previous screenings that were done using an older version of the handbook.
So they're building on existing knowledge.
Right. And the report also mentions some real-world RVS programs that have been carried out in places like Oregon and Utah.
So these aren't just hypothetical examples. These are actual programs that have been implemented.
Right. Both states focused on screening school buildings because they had a lot of older structures that predated modern seismic codes.
And I bet they found some pretty concerning results.
They did. In Utah, for example, they found that a significant percentage of schools were at high risk of collapse in a major earthquake.
Wow, that's scary. And what happened then?
Well, that information was used to push for more funding and resources to address seismic safety in schools.
So the RVS data actually led to real action.
Exactly. And that's one of the most important things to remember about RVS. It's not just about gathering data. It's about using that data to make informed decisions and take steps to reduce risk.
Absolutely. So what are some of the ways that RVS results can be used by communities and authorities?
Well, one of the most common uses is to develop mitigation programs.
Mitigation, so like ways to reduce the risk.
Exactly. They can use the RVS data to prioritize which buildings need further evaluation and potential retrofitting.
So they're focusing on the most vulnerable structures first.
Right. And they can also use the data to create comprehensive building inventories, which are really useful for things like disaster planning and risk modeling.
So they can get a better understanding of the overall risk profile of the community.
Exactly. And they can use this information to inform land use policies and building code updates.
So it can actually lead to changes in how buildings are designed and constructed in the future.
Exactly. And RVS data can also be used for post-earthquake assessments to quickly identify buildings that might be unsafe to occupy.
So it can help with the recovery process after a disaster.
Right. And it can be integrated with systems like Shakecast, which uses real-time data to estimate damage and prioritize inspections.
So it's a valuable tool throughout the entire disaster cycle, from preparedness to response and recovery.
Absolutely. Now, as we wrap up this deep dive, what are the key takeaways you would want our listeners to remember about rapid visual screening?
Okay, so I think the most important thing is that RVS is a crucial first step in understanding and mitigating seismic risk in a community.
It's a fast and relatively inexpensive way to get a handle on which buildings might be the most vulnerable.
But it's important to remember that it's just a preliminary screening. It's not a guarantee that a building is safe or unsafe.
Right. It's a way to identify those buildings that warrant a closer look from a qualified engineer.
And the process is very systematic. They start with careful planning and data collection, then they do the field screening using a specific scoring system, and then they use the results to inform decisions about mitigation and other actions.
Exactly.
Yeah.
It's a well-defined process that's been refined over many years.
And it's not just about protecting buildings, it's about protecting people.
Absolutely. The ultimate goal of RVS is to save lives and reduce injuries during earthquakes.
For me, the most surprising thing about RVS is how something as simple as a visual inspection can have such a big impact.
Right. You're basically looking for clues that might indicate a hidden weakness. And that can trigger a whole chain of events that could ultimately save lives.
It really highlights the importance of having these early warning systems in place.
Exactly. You can't fix a problem if you don't know it exists.
Ah.
And RVS helps us to identify those problems before it's too late.
So for you, the listener, think about the buildings you see every day. Try to imagine how they might hold up in an earthquake. Do they look sturdy or fragile? Are they old or new?
And maybe even take a look at a seismic hazard map for your area. It's a good reminder that we live in an earthquake-prone world, and we need to be aware of the risks.
Absolutely. And one final thought to ponder. As technology continues to evolve, how will it change the way we assess and mitigate seismic risk? Will we see even more sophisticated screening methods in the future?
It's an exciting and challenging field, and I think we can expect to see some major advancements in the years to come.
Thanks for joining us for this deep dive into rapid visual screening. We hope you found it informative and insightful.
Stay safe out there, folks. And remember, be prepared.